Hello everyone, we are Team 7 and today we are presenting our guardrail based hallucination detection and prevention system for drug information chatbot. Our goal this semester is to extend last semester's LLM enrichment pipeline into a real-time guardrail driven healthcare chatbot using modern open weight LLMs. I'll briefly introduce the problem and the objective to you. So, large language models often generate confident but factually incorrect information known as hallucinations. In healthcare contexts, this can be dangerous. Our objective is to build a guardrail enabled drug information chatbot that uses DrugBank as a grounded knowledge base, retrieves evidence before answering, scores the response using guardrail checks, assigns a confidence score, and decides whether to allow, warn, or block the response. So let me walk you through our system architecture. As you can see, this is our full end-to-end architecture where the healthcare user submits a question in Streamlit UI. The query processor normalizes it and logs the request. The retrieval module fetches top key evidence from DrugBank gold tables using FAISS. Selected LLM generates an answer, and the guardrail module computes grounding similarity, entity overlap, policy rule checks, and confidence score, which is either 0 or 1. Based on that, the decision engine either allows, warns, or blocks the answer. Everything is logged into our matrix database and shown in the analytics dashboard. This builds directly on our previous bronze, silver, and gold pipeline. For data ingestion and pipeline architecture, we use DataBank XML dataset containing approximately 20,000 drug records and 250,000 interaction entries. Our ingestion pipeline follows a lakehouse pattern. Bronze layer for raw XML stored in object storage. Silver layer for parsed, clean, a normalized structured dataset. Gold layer for validated tables with schema compliance, and feature preparation where embeddings are generated and FAISS index is built. So data cleaning steps include removing HTML tags, normalizing text, standardizing drug names, removing duplicates, and enforcing schema validation. And after pre-processing and cleaning all this, we got 13,742 valid drug entries, 242,380 interaction pairs, missing values reduced from 18% to 4%, and 99% of the schema compliance was met. So this ensured high quality grounding for LLM retrieval. As you can see, these are our pre-processing results. Next, talking about training and test data preparation. So to evaluate model fairly, we constructed a controlled QA dataset which contained 200 curated drug-related queries balanced across dosage, side effects, contradictions, interactions, and edge cases. So we split the dataset into 120 queries as development set for guardrails threshold, turning, and 80 queries for held out for test set. So each response was manually labeled as fully supported, partially supported, and unsupported, which is hallucination. We also labeled guardrail decision as allow, warn, or block. So this ensures objective evaluation. Now talking about the data analytics results, here are our quantitative findings. As you can see from the bar chart, our hallucination rate for Llama was 12%. Mixtral was 10%, Gemma was 9%, and Phi was 18%. This shows that Gemma performs safest, while Phi has the highest hallucination risk. Talking about latency, we can see that Phi is fastest. It is 160 milliseconds mean. Mixtral provides strong balance between speed and accuracy. Next, we can see from the graph, we can see that guardrail ROC curve. AUC values range from 0.82 to 0.90, which indicates strong separation between supported and unsupported outputs. Overall, the guardrail significantly reduces unsafe outputs across all modules. These are our results. Now, talking about LLM comparisons, so we compared 4 different open weight LLM architecture. First is Llama, which is a dense transformer baseline. Second is Mixtral, which is mixture of experts. GEMA, which is alignment focused, and 5, which is a synthetic curriculum trained model. The key insights which we got are that Mixture achieved highest factual accuracy, which is 87%. GEMA had the lowest hallucination rate but higher refusal rate. 5 was the fastest but highest hallucination risk. And Guardrail AOC above 0.82 was observed for all the models. So we can see that architecture and training philosophy clearly influence hallucination behavior. Now, talking about what we did last semester and what we did this semester, we can say that the last semester was our baseline, but this semester we actually implemented a lot of things on our baseline. We have implemented a working streamlined dashboard where user can select different models, view guardrail decisions, inspect evidence and confidence score, and compare quantitative metrics. We'll now demonstrate the system.
Hi everyone. In this demo, we are representing our Guardrails project, a medical drug safety guardrail chatbot system. I will show you the data pipeline, which includes ingesting drug bank XML, create bronze and silver datasets in MinIO, run data quality checks, promote clean silver, and export, train, val, and test for modeling. Now I will show the containerized infrastructure we use to run the platform. The MinIO for S3 storage, Kafka for streaming support, and Airflow for orchestration. The MinIO is our S3 compatible storage layer where all bronze, silver, and raw plus clean datasets are stored. We do have Kafka here, which includes support for event streaming pipelines for future real-time updates. Here our main focus is on the batch lakehouse pipeline, but Kafka is running and available. Airflow provides orchestration orchestration so we can run an ingestion and processing steps as scheduled. So coming to the first step, we run MinIO as our S3 compatible data lake, as I told earlier, where Sparks writes bronze, silver, clean silver datasets into MinIO buckets. These are our buckets: bronze, silver, and gold. So next, coming to the ingestion pipeline, first we pass the let me take you to the terminal. First we pass the drug bank XML using Spark and land it as a bronze Parquet file in the MinIO. Here you can see that the raw XML drugs Parquet file is landed in the MinIO bucket. Second, we need to transform the bronze data into a cleaner silver dataset. This is where we normalize fields and standardized structures. So you can see in the terminal here, firstly we have loaded successfully the raw XML files, which are 18,104 Parquet files, and then we transform the bronze into a clean silver dataset. You can see it here. The silver flattened row count is given, which is 22,428. So we have flattened this and polished and successfully returned this into the silver bucket. I can show you the MinIO window here. See, in MinIO, in bronze bucket, we have a silver folder where we have this drugs clean, and we can see that it's a delta table. So next we run the DQ enforcement. We run the DQ enforcement rules to split clean and versus problematic records. We store good and bad outputs locally and created a summary report. We can see that the bronze input count was 18,104, like silver output count was 17,430, and the duplicates removed, and we stored that in the S3 delta bucket, which is bronze silver drugs, which I showed you earlier. And it is also stored locally on in our silver directory under silver underscore drugs.parquet file. So we promoted the good dataset into the canonical clean silver data table. This is the version used for analytics and modeling. We can see this in the mean IO environment, like mean this bronze, silver, this drugs clean. This is the good dataset which we use for the canonical, like for more analytics and delta training. Further, we also exported this dataset for fine tuning, and we created a reproducible train val and test split for the new updated new model. Thank you. So this is our progress of the project so far, and we are currently working on the Streamlight application, which is our chatbot. So this is where we are now, and we are trying to improve its accuracy and score for the outputs it generates. Thank you.